Hello guys, I hope that everyone is doing very well today. So today in this video I'm just going to make you learn how to implement the basic programming assembly language to program the AVRs. So we have to do just three examples here. So the first here is to program to a first we have to just clear the bit and then add 10 times to the R20th register and send the sum to the port B, and then using the zero flags and B, R and E commands. So first line here is to just use the load data immediately to the R16, that is 10. So this line will do or work as a counter, so it will execute it 10 times for the decrement, and here we'll see that after that the R20 here is loaded with the 0 value, and the R21 is loaded with the 3 value, and there is again label and then add 20 and 21. So here you will see that initially the value of 20 is 0 and the 21th is 3, and after you can see that the decrement of R16 here is called, and you will see that the decrement from 10 to 1, so this loop will repeat 10 times, and BRNE command will bypass when the 10 time loops will be done and the output at the port B will be appeared. So this is basic and simpler construction for to show you how these commands are working. This is add mega 3 to 8B, and the two 7-second displays are here, and one thing to be noticed here that the gray colored boxes here are showing that it is neither 1 or neither 0, so it will work, it will not work. So we will just guess these values in hexadecimal and then convert them into the suitable form, and I'll let you know how does it working. So after the VSM debugging, here we'll see that there is no cycle and all the registers are initially 0, and after that loading the value 10 to the 16th register, the first cycle has been repeated. After that the 16th register is loaded with a value of 10, that is A in hexadecimal, and after that you will see that the R20th register will also be loaded with 0, and there is it doesn't make any difference, and after that the 21st register will also be loaded with the 3 value, and here you can see that, and after that the sum will be done and that will be saved on the port B R20th. So R20th value is this, because you can see that 0 plus 3 is equals to 3, so 3 is stored here, and again repeating the loop 10 times and clicking in such a way that it will complete the loops, and after complete 10 times executing this loop will go to the out and port B. So port B R20th register will store 1 E value, and similarly we will see towards what happened here, and completely simulating that part. We will see that 0001 means that it is 1, and 111 and 0, this is equivalent to E in hexadecimal. So after our first example has been verified, and we will now move on towards the next one, and here it says that the minimum number of the times maximum number of the loop that can be repeated in the 8-bit register will be of what value. So as we already know that in hexadecimal it is FF, means all the bits are already filled with 1 value, so the loop will be repeated to 2 raised to power 8, means that 256, from 0 to 255, means that the loop will repeat 255 times. After shifting towards the example number 3, the statement is just like that, to load the port B register with a value of 55 and then compile a complement of the port B 700 times. So we'll take the complement 700 times to the port B in which we have registered the value of 0x55, and here we'll see that I've just coded here, and we have just loaded the R16th register with a value of 55, and output at the port B with the register 16 is appearing, but Here the 20th register is also loaded with the 10 value, and these two loops are fabricated in such a way to create the nested loop. So here is a nested loop that can be multiplied with each other to form the 700, means 70 into 10 times is equals to 700. So after every 70 times repeatance in the loop, the R20th register will decrease its value by 1. So these two loop 1 and loop 2 labels are here, and the this is the complement of R16. So the complement of R16 will be done 70 times, and the out at the port value of 16 will be appeared here, and the decrement of R21 will be done. After that, brne command will be executed, and if all the loops have completed its cycle, then this will be bypassed, and then it will go towards the R20. Similarly, I have just explained the previous, and then it will jump out of the loop and complete all the segment, and the complete debugging. So here we will see that simulation is running, and so I have to just stop the VSM debugging and then again start the VSM debugging. So it's showing the simulation is running. So here you can see that at the first cycle there is no any value stored here, as well as if we go towards the schematic capture, you will also see that there is no any type of LED or the logic state appearing at the legs of these LEDs. So here is the complete debugging, and here we'll see that the registers are here and they are completely showing themselves as well, and the screen is not quite appearing very well, but we'll see that after completing one cycle it will show you nothing, but after just completing through 3 to 4 cycle, it will just store the value of 55 in the register 16, and then the R20th register will be loaded with the value of 10, and here you will see that the R20th value will be stored after completing through the entire process. So I have to just expand this and we'll let you know. And here you can see that the R20th register just stored the value of 10, that is in hexadecimal, is equals to 0A, and after that 21th register has stored the value of 46, that is this loop will be repeated 70 times, and here after again, so it will repeat many cycles, means that 700 after 700 cycles this loop will be completed. So this is entirely a difficult task to again click and click and click. So these values will be changed, as here you can see that R20 and 21st and 16th registers will also be changed according to the repeatances of the loops. So while going towards the value, and here you will also see that the value is also changing. You can see that 0101 means that it's 101 is equivalent to 5, and it's also equivalent to 5. So at this time the value of 55 is appearing above these LEDs. These are not showing themselves properly because there can be any errors in the simulations or connections, and also the pins are not connected with each other properly. So in order to connect them properly, we have to make the board of Arduino as well. So moving towards the third code, here you will see that its statement is just like that. We have to just create a program to determine if the location 0x200 contains a value of 0, but if it's containing the value of 0, so we have to insert 55 into it. So first we have to go to the code, and here we will see that equ malloc is equals to, this line is basically has been created by the creator, because .equ is a particular code or command to assign the values to the alphabetical names that are being the user defined. And again, here I have loaded the data immediately to the R30 register, and then stored it in the value of malloc, means that my location. And after that I have tested R30, means that if it will be equal to 0, then this will be bypassed and loaded the data will be R30. So if it is equals to 0, then this command will be executed. So as you already know that the empty IC is always 0 if it is reset, so it will be 0, so this will be bypassed, and then you can see that R30 will be loaded with the value of R55 and STS malloc R30. So the location that is 0x200 will be loaded with R30 register value, means that the register is shifting its value from its own value to the malloc location. So this is the entire work for today, and I hope that you really enjoyed this video. But if there is any queries related to the part, you can comment me in the comment sections. I will let you know. Thank you.